Bismillahirrahmanirrahim. Assalamu alaikum. Welcome back. We are in the series of CREST conformational analysis and properties calculation videos. So in the last video, we learned how to do a conformational analysis and get the conformers from by using CREST. So now we are going to learn how to use this CREST ensemble file and separate the conformers and then create files from them to run optimizations and other calculations. So I'll just copy this file and make a new folder, conformational analysis done, whatever you want, and I will paste it here. So what happens now is I will also make a folder for separated conformers. And what we will do is we will now use a Python script. So I will first come to this folder, and now if I ls, I can see these files. So I will just create a file called some script. So first, let me show you the script. So I told you about my GitHub scripts repository. And if you come here, I do have a folder called CREST scripts. And here I have a script called CREST Conformational Separation.py. So I will just create this file here, which is an empty file at the moment. And then I will open this script and I will copy this whole script, Control C, and paste here. So this script is now saved. And in the meantime, I will also save this second script just so that we can use it later on. And this is called make opt or NMR calculation from Gaussian. It's not letting me copy the name. I will copy it from here. So I will now just touch this file. Here is the file. And then I will, so these instructions also tell you how to use things. So yeah, this is the script for the further setup. I will tell you about it later on. So I've saved both of these scripts now. And now we are going to learn what to do with these scripts. So now we will use the CREST conformer separation script, and I will actually use it in separated conformers. So you can move the CREST ensemble inside, or if you want, you can keep it here. So I will run the script in separated conformers so that the files get separated in the folder and not here. So what I will do is I will run Python 3 and then the script name. So the script is not in this folder, it's one step back. So I'll say // CREST conformers separation.py, and then I will tell it the path of the ensemble, crest-ensemble.xyz. So I'll make it to show everything on one line. So when I press enter, it tells you all done. Total conformers saved 33 and energies saved in conformer energies.csv file. So if I open this file, I'll just show a list so you see all the 33 conformers, and if you open them in JMOL, you can see these are different conformers. And then you got a file with their energies as well. So if I open this file, you see file name and then energies in the atomic units. So if you want to see the relative energies, I can see energies, relative energies, and then I can say this one minus $B $2. So it means that I want to minus this from this, and then every other energy from this energy to see. So if I double click it, and probably I'll, so this is actually atomic units. So if we say relative energy in, let's say, kilojoule per mole, here we say it's AU. So what we can do is just multiply this by 2625.5. And now if I copy it, you see that I'll center it. So these are the energies in kilojoule per mole for the conformers. And I can actually save this file as an Excel file now. So if I save it as Excel workbook and click save, it will save the energies in an Excel file because CSV cannot like do the formatting and stuff. So I just saved it in an Excel file. And I can move this file to here to keep things simple. And now we have another script which can create input files for you so that you can run them and then do further conformational analysis on them. So what this script basically does is if you open it with Notepad, I'll tell you, don't worry about everything else. You just need to look at this section, the write Gaussian file. So this is a function basically where it is writing a Gaussian file. What I have done is I have included three files together. So it produces a checkpoint file name and then a route card section. Route card is defined below. I will tell you about it. And then it writes the title and then charge and multiplicity and then geometry. So I have also have a pseudo potential in here, which actually I used for a molecule which had the heavy atoms. But since we're not going to use it, I will just comment this line here. So basically, you can edit this script according to your needs. So I will actually comment this line everywhere so that you don't have to put the ln L2Ds at pseudo potential. And then it will print a link one. So there will be another calculation. First will be optimization, and then I will calculate the optical rotation. Basically, optical rotation will tell you also about the structures, like if they are similar or not. It's a good way to look at the structure because this is a really sensitive value and it can tell you if two structures are identical or they are a bit different. So then I will calculate the NMR. So you can do all these things for a natural product together. You optimize, calculate optical rotation, and NMR in one calculation. So if you come down, here are the route cards. You can change them according to your needs because I removed the pseudo potential. So I will just remove this keyword pseudo is equal to cards from here and from here as well and from here. So now what is it doing is optimizing using B3lib, and I will also remove this gen keyword with with a basis set now that I had earlier. You can put any basis set of your choice, and I had this basis set for NMR. So now these route cards are according to our need. This will calculate the optimize. It will optimize the molecule, and this will calculate the optical rotation in solvent chloroform. And then, if you want, you can change the solvent here and here. Then it will do an NMR calculation. So these are three route cards that are actually defined here. So let's save this script. And first we run it on one file here and see if it works perfectly. Then we can run it on all the files. So what I'll do is Python 3, and then I tell it the script name, and then conformer 01.xyz. So I'll just run it on one conformer. It has made its COM file here. If I open it, I can see that this is the optimization and then link one, but it didn't put a new line here. So that is a problem. and not a new line here as well. So we will fix it because it was being done by the pseudo potential that we removed. That's why. Now we'll first fix it. So what will we do is before link one, I can just say \n. It will put a new line. And then here as well, \n. If we save it and then run again, and we will have a look now. So now you see here is a new line, link one, and then a new line, and this calculation for NMR. So this way you have linked files which are in one COM file. So now what will we do is we will run this command on all of the conformers. So I'll just clear it. And now we will do it for in star dot xyz and do Python 3 dot slash make opt or NMR calculation, and then I will say $I, and then I'll say done. So if you want to learn how to use these for loops in Bash, you can watch my videos on about Bash and Linux. I have told about in detail about how to use a command and loop. So what this command is basically doing, it's running this Python script for all of the XYZ files. That's the simplest thing. So if I press enter now, you see it has made all the COM files. So now you can even sort it. If I make mkdir all COM files, and then I can move start.com to all COM files. And here we have COM file for all the conformers now. And if you run them, they will generate log files for each of these conformers. And when you have the log files for all of them, then we have to extract the NMR data and do further analysis. So I will tell about it in the next video. How can we do the analysis, and how can we compare the NMR, etc. for this molecule? So I hope you got how to use these scripts to make your life easier and do things real quick. And if you have any questions about it, you can post in the comment section, and I'll get back to you as soon as possible. Thank you very much for watching. Bye bye.